Now we want to talk about spin quantum numbers. Nuclear spins have two kinds of quantum numbers: a principal spin quantum number and a set of spin projection quantum numbers. As is said on the slide, every nuclear species is associated with a principal spin quantum number, I, which can either be a whole integer or a half integer. There's a way to work out if it is a whole or a half, but this is not important for us to learn for this topic we are teaching. All we need to know here for this study is the correlation between a principal spin quantum number and the observed peak coupling patterns. Nuclei can be classified in terms of their principal spin quantum number. For example, the principal spin quantum number for 1H is a half, and for 2H is 1. And hence we call them spin half nuclei and spin 1 nuclei, respectively. The spin projection quantum numbers, MJ, are a set of numbers that can be worked out by a formula with I, as shown in the slide. They start from minus I, increasing by 1 consecutively until it is ended by positive I, as indicated on the slide. About 30 species of nuclei are spin halves, which include 1H, 13C, 15N, 19F, 29 silicon, 31P, etc. It means that their MJ can only have two values, minus a half and positive a half. Because minus a half plus 1 is positive half. And that is the N value for the set. Spin-I nuclei, such as 2H's, 6 lithiums, and 14 N's, have 3 MJs, minus 1, 0, and 1. This statement is important. Every MJ is associated with a nuclear spin energy level and a quantum state, which implies that there are only 2 allowable or probable energy states for spin half nuclei. Note that the word probable is used here to clearly indicate that every nucleus has a probability to be in one of the 2 states at equilibrium. And we are going to talk about this in the next slide. And finally, for simplicity, only spin half nuclei will be discussed in the following context. What do we need to learn about nuclear spin energy for our study? The first statement tells us that nuclear spin energy can be calculated by MJ and their precessing frequency as follows, i.e., EJ equals MJ times V0 times H, or MJ times omega naught times H, where H is the Planck's constant, and the value is approximately 6.63 times 10 to the power of minus 34 joule second. And h bar, being reduced by a factor of 2 pi, is called the reduced Planck's constant, and the value is approximately 1.05 times 10 to the power of minus 34 joule radian. Note that the unit of V0 is Hertz, which is 1 over the time second, or cycles per second. And hence the unit for the multiplication of it with H is joule, which is the unit of energy. The multiplication of omega naught, which is in radians, with h bar, also results in the energy unit joule. One way to remember h bar is to think of the bar being a symbol of division, i.e. the h divided by 2 pi. In a magnetic field, spin half nuclei have 2 energy levels, which corresponds to 2 energy states as shown by the graph on the slide, where the lower energy level corresponds to mj equals minus a half, and the higher energy level corresponds to mj equals positive half. In other words, nuclear energy levels are directly proportional to the angular frequency of the spin, either positive or negative. What is the importance of delta E? In NMR theory, a quantum of energy is transmitted when the energy status of a nucleus is changed from one to another, which is equal to the difference of the energy levels, delta E. It is easy to work out that delta E, being E2 minus E1, is equal to V0 times H, or omega naught times H bar. If we use the quantum energy unit, either H or H bar, the transmitted energy is then simply V0 or omega naught. In other words, the amount of transmitted energy in terms of quantum energy unit is equal to the angular frequency. This is in fact a general formula for us to work out NMR frequency in quantum mechanics. The next thing to learn is Boltzmann distribution, which is a law that governs the intensity of NMR signals. Be aware that Boltzmann distribution only applies to the situation in equilibrium state. It says that in a system having several energy states, the probability Pj of an element being in a certain state depends on its energy, Ej, and temperature, T, in Kelvin, such that Pj is directly proportional to e to the power of minus Ej divided by Kt, where K is the Boltzmann constant and the value is approximately 1.38 times 10 to the power of minus 23 joule per Kelvin. In physics, a law means something that cannot be changed. It is a fully proved and verified Mother Nature. In brief, the probability of being in a certain state depends on the element's energy level and temperature. For an NMR experiment, the temperature is unchanged, so the probability of being in a certain state only depends on the spin energy. We knew that the number of allowable or probable spin energy levels is limited by the number of quantum projection number Mj, M for mother. So is the number of different populations Nj's, N for nanny. Therefore, at any instance, the ratio of the population in different energy states must be equal to the ratio of Pj's, the probability for each individual to be in one of the energy state, i.e. N1 over N2 over N3 and so on is equal to e to the power of minus E1 divided by KT over e to the power of minus E2 divided by KT and so on. Spin half nuclei only have two energy levels, and hence we only have one ratio, which is N1 over N2. And it's equal to e to the power of minus E1 divided by KT over e to the power of minus E2 divided by KT, and it's equal to e to the power of delta E divided by KT, or e to the power of V naught H divided by KT, where delta E is equal to E2 minus E1 and equal to V naught H, as shown in one of the previous slides. Further inspection of the right-hand side tells us that the exponent of the base is much less than 1, where the order of magnitude for the four parameters V naught, H, K, and T are 10 to the power of 8, 10 to the power of minus 34, 10 to the power of minus 23, and 10 to the power of 2, respectively. And hence, the order of magnitude for V naught H divided by KT as a whole is 10 to the power of 8 minus 34 plus 23 minus 2, i.e. 10 to the power of minus 5, which is less than 1. The expression can then be simply simplified by Taylor expansion, which says that e to the power of x is equal to 1 plus x divided by 1 factorial plus x squared divided by 2 factorial plus x to the power of 3 divided by 3 factorial, and so on. Where a factorial of n is a product of all positive integers that are less than or equal to n, For example, 3 factorial is 3 times 2 times 1. Apparently, for an x that is greater than 0 and much less than 1, only the first 2 terms are significant, i.e., e to the power of x is approximately equal to 1 plus x. For example, the square of 10 to the power of minus 5 is 10 to the power of minus 10, i.e., a 10 decimal figure leading with 9 zeros in the decimal, which is extremely small, of course, and can be ignored. The population ratio N1 over N2 then becomes 1 plus bracket V naught H divided by KT, which is slightly greater than 1 because it is 1 plus something very small. This tells us that N1, the population in lower energy state, is always greater than the population in higher energy state, N2. Which makes sense because it meets the second law of thermodynamics, i.e., the principle of minimum energy, which is another law of the mother nature. Okay, in this slide, we are going to explain 2 relevant concepts a bit further. First is about the symbol N. It has been used in many NMR articles, often unclear what it refers to, and hence it needs to be clarified. Although conceptually they are very simple, but understanding the N used in NMR formulae often needs a bit of thinking. We know that for spin half nuclei, there are only 2 populations, and hence N total, the total spin population, is simply the summation of all N's. N net, on the other hand, is simply N1 minus N2, which is the net spin population. We know that the magnetic moment of spin-up population are always cancelled by those of the spin-down population, and hence only the net spin population contributes to the observable NMR signals. Therefore, we need to figure out how to increase the net population so that the intensity of NMR signals can be improved. It can be derived that N net is directly proportional to N total, to gamma, and to B naught, but inversely proportional to the temperature T. You can see my chapter 2 for more details. This relation is important for us to figure out a few other formulae involved in NMR theory. The fact stated in this slide is simply drawn from the correlation above. Let's move on to see the next slide for more explanation and applications.